Welcome to Chemical Process Safety. This video is about pressure relief placement and selection. So thinking about the scenarios in which we might have a high pressure situation arising, it could be because our process is not inherently safe. So that would be the first thing that we would attempt to fix about that. We talked about that way back at the beginning of the course. Another scenario would be that we've lost control of the process. And so improving the process control would alleviate the possibility for that high pressure situation to occur in the first place. Therefore, that would be the second line of defense. So the first point to make is that pressure relief valves are absolutely not the thing that you would expect to be the primary means of preventing against a high pressure situation and a potential explosion. It's important to note that this is the absolute last line of defense, and if all other things have failed, this would be the last possible thing that would alleviate the situation. And the reason for that is because when a pressure relief valve opens or discharges material, well, when it opens, it does discharge material, and that can lead to problems in and of itself. So if you had a pressure relief valve, you might need some secondary containment, for example, if it was a hazardous component, because you wouldn't want to release that to the environment because, as we've seen in the dispersion models module, that material can travel. Or it could be flammable, or there's any number of different problems. So again, pressure relief valves are not perfect, but they're the last line of defense. So if you want to design a proper relief system, you should ask yourself four main questions. The first is, where should these relief devices be installed? The second is, what type of relief devices would be the most appropriate? Third question is, how large should those relief devices be? And as I mentioned just before, what is going to happen to that ejected material? Are we going to contain that somehow? Are we going to scrub it? Are we going to flare it? We shouldn't just, say, oh, the pressure's relieved and therefore there is no problem. So let's go through these various types of questions. Let's start with the first question: where should the reliefs be placed? There are a few guidelines for placing the pressure relief devices. First is that all vessels need a relief. So this includes reactors, heat exchangers, columns, mixing tanks, everything. Blocked in sections of pipes carrying liquids which may be exposed to heat or cold. There's a CSB video I usually like to show. It was about a dead leg in a pipe, and over the winter time, I guess it had froze. There was water in the pipe, and it was very cold, and so it froze and it expanded a little bit, and that led to problems in the summertime when it thawed back out. Pressure reliefs need to be placed on positive displacement pumps, compressors, and turbines, always on the discharge side. For reasons from fluids, a positive displacement pump is going to increase the pressure, and therefore on the discharge side, the pressure is going to be higher there generally in the pipeline. Storage vessels are a special case. They actually need pressure relief and vacuum relief. And then vessel steam jackets on reactors also need reliefs. So I've got a quick exercise here. And we have a P&ID, piping and instrumentation diagram. Before we think about where the pressure relief should go, let's just talk through what's happening here. So it's an exothermic batch polymerization reaction happening in vessel R1. It'll start by pumping initiator in. So that occurs through this pump. So we're going to pump in some initiator. We start with the monomer in the vessel already because it's a batch reaction. Then we're going to heat this reactor. So we do that by the steam jacket. So steam is going to come in this way through valve V4 into the steam jacket, and then it is going to exit this way. And then once the temperature is up to 240 or whatever it is, then we want to not heat that anymore, but we want to cool it because it's exothermic. So that occurs here. So we're going to pump in cooling water through this pipeline, through the cooling jacket, and then cooling water is going to come out. This is a heat exchanger. So we've got hot cooling water. We're going to cool it. It has warmed up. So we're going to need cooling water to cool down the heated cooling water that comes out of the reaction. and then we're going to pump it to a drum, and then that just exits the process. Probably goes to the cooling tower or something and gets recycled somehow. We also have nitrogen here that is going to inert the headspace. So again, we've got a check valve, we've got a control valve there. Pressure controller is what this PC means. And I guess we also have a pipeline for monomer in, but this is only going to be used at the very beginning of the process. So you can see why I had this video on how to read a piping and instrumentation diagram, because it could be a little bit confusing, at least at first, to figure out what's going on. Oh, this LC, remember, is a level controller. So it's going to read how high the liquid level is. And then presumably it's connected to this pump by an electrical signal. Once the level gets to be a certain height, it's going to tell this pump, hey, you have to turn on, because that's going to drain the liquid out of this drum D1. So pause the video here, see if you can use the rules, and just briefly going through them. All vessels, all blocked-in sections of pipe, positive displacement pumps, storage vessels, and vessel steam jackets all need relief. So again, pause here, see how far you can get. And I've already got mine. And I've color-coded it based on the rules. So all vessels need a pressure relief. I count 3 vessels in this diagram. We've got the reactor, R1, we've got the exchanger, E1, and we've got the drum. And notice I'm using the icon for a pressure relief valve. We haven't talked about it, but that'll be the next question. What type of pressure relief do we use? Rupture disc is another option, and that has a different icon, remember. 2 would be blocked-in sections of pipe. I didn't see any blocked-in sections of pipe in this particular diagram. Really blocked-in, it's hard to think of an example of when you would see a blocked-in pipe. A lot of times it happens in real processes because it's like an old section of pipe and the process has been reused or repurposed in a certain way, and then a section of pipe becomes redundant, and so that's why a pipe would be blocked in. You wouldn't necessarily design a process with a blocked in pipe in mind. At least I don't think so. Rule 3 is positive displacement pumps on the discharge side. So we've got P1 there. Looks like I missed or it got cut off, but I should also have one on P2 as well. Storage vessels, I don't have any. I guess you could argue that D1 is a drum, but it wasn't necessarily clear to me in the context of the story, or I didn't make it clear that this was a storage vessel. But if it were a storage vessel, I would also need a vacuum relief in addition to the pressure relief. And then steam jackets need one as well. So there's not a really good place to put it here, but it's all connected. So as close to the reactor as you can on the steam jacket. All right, let's talk about the second question, which is the type of pressure relief devices. Got into this a little bit in the last video. But simplest and the most mechanically sound is going to be the rupture disc. This is a simple sheet of metal that is designed to rupture at a certain set pressure, and that is set by the manufacturer. So you can buy a rupture disc, for example, that would rupture at, I don't know, 10 PSI gauge or whatever it is. These are cheap. They are easy to replace. They do not leak, foul, or plug. So again, simplest option that will get the job done. The problem is that once it is open, it stays open. So it's easy to replace, but that's because you probably will have to replace it at some point if it ruptures. And the other issue is that it stays open. So if there's a lot of material that is being discharged, it doesn't seal up again. So if you are going to clean this up afterwards, you'd have to wait until all the material was discharged so that the emergency responders would not be put in danger. Option number 2 is a conventional spring-operated valve. So this is kind of my cartoon based on what is in the book. We had a little bit more detail, but the red here is a spring, and the tension of the spring sets what the set pressure of this valve is. The benefit of this one is that once the pressure is relieved and the pressure drops down below the set pressure, the spring kind of pushes this gasket back in place, and it plugs up the pressure. Plugs up the vessel again. So this problem that we had of the ruptured disc staying open is alleviated. And another benefit here, I guess you have the same benefit with the rupture disc, is that you can route this to some sort of pipe to a secondary containment system. So it's not like it's open. It's a little bit more complicated, I guess, for the rupture disk case to have that in a pipeline. Oftentimes you see ruptured disks just discharging to the environment. The pros of the conventional spring operated is that it's reliable. Again, it's going to reseat when the pressure drops back below the set pressure. However, these tend to be a bit more expensive, just a tad more complicated than the rupture disk. And the other problem is that the relief pressure could be affected by the back pressure, which is the pressure that is downstream. So imagine if you've got high pressure here, the relief valve opens, but then your secondary containment actually, if the pressure starts building up in your secondary containment, well, now you've got to force back on this plug again, which is going to affect the set pressure. So that extra added complication does kind of mess with things a little bit and make it a little bit less reliable. A third option, which is related to the conventional, is the balanced bellows. So check the textbook for an example of what that looks like. The benefit of the balanced bellows is that it is vented. So instead of being sealed here, the pressure on the outside is always atmospheric. That alleviates the concern that the pressure is going to be affected by the back pressure. And the spring would be protected from corrosion since the material that it is discharged is never going to be sitting on there. The cons of the balanced bellows is that it's the most expensive of the option, and the bellows may fatigue or rupture. And in that case, material could be discharged to the atmosphere. So I've only answered the first two questions, but I'm going to leave it here and come back and address the last two questions in the next video.